ball, and this ball, and I just dropped this ball, and this ball will fall downwards, and it will go faster and faster. Now I'm going to think of the downward direction. Let's see. I'm going to think of a downward direction like this as the direction of the x-axis, where the starting position is x equals to 0. So I'm choosing a direction that is positive going down and negative going up. So in this case, x would be my displacement. If I think of sketching a graph, let's sketch a graph of how x, the displacement, changes with time. Let's think about that. Starts at x equals to 0, and as time passes, the ball falls faster and faster. So we would expect the graph to look like this. It sort of goes up, and the slope will keep increasing, because as we remember, the slope of a displacement graph is actually equal to the velocity. Right? If I think of a small interval in time, right? If I draw say consider the slope on one part of the graph, then for a small interval of time over this interval, which I call delta t, the stone or the ball would have fallen by a small distance delta x, and the gradient is given by delta x over delta t, which is the velocity. The velocity is given by the distance, the small distance moved in a short time, delta t. And it so happens that these are the vertical and horizontal, so this is also the gradient. Alright, and as the speed increases, the gradient gets steeper and steeper, as we can see. If I now think of sketching a graph of the velocity against time, let's see what that might look like. Let me draw the axis for that. This is time and that is velocity. Now if I want to think of a graph of velocity against time, let's follow this displacement graph starting from here, starting from time t equals to 0. Now at this time, when I just dropped the ball, as you can see, the gradient is horizontal at first. It just means that the ball starts with a 0 velocity. And as time passes, the slope increases. The gradient increases, graph gets steeper and steeper, and it means that the velocity is increasing. So I can imagine that if I want to sketch or plot the graph of v against time, in the beginning, when I just drop the ball, the velocity will be 0. So I'll be starting at 0. And as time passes, right, the v will increase. Okay, v increases, something like that, and the graph would then look like an increasing line or curve. Okay, so for now, I'm just going to take it that the velocity graph increases in a straight line. Now later, we understand why when we learn more about forces. Forces accelerating the ball. So for now, I'll just take it that the velocity goes up in a straight line. Now, for this velocity time, from this velocity time graph, I can think about the acceleration. Now, let's say I think about a short time delta t, short time interval delta t. So over this short time interval delta t, the velocity increases by a small amount, increases by, say, for example, delta v. So I'll call it. Now we already know that acceleration is equal to the change in velocity. Now I've written previously, I've written this as v minus u over the time, final minus the initial velocity. So v minus u is just the change in velocity, which in this case is delta u and delta t. So for this particular example, this acceleration is also equal, can also be written as delta v, change in velocity, over the time interval. Okay, which is actually, as you can see from this triangle here, this right angle triangle here, since delta v is the vertical side, delta t is the horizontal side, is also the gradient of the graph. Okay, gradient. Also, we have two gradients here. In the first case, this we say that velocity is a gradient. Well, actually, it's the gradient of, to be quite clear which graph we're talking about, is velocity is the gradient of the displacement plotted against time. We call that the displacement time graph, which is this one here, where we plotted x against t. And we have just seen that acceleration is also equal to a gradient, but this gradient is the gradient of this graph, the velocity time graph. So acceleration is equal to the gradient of I'll write this now, of the velocity time graph. Okay, now once we have this idea, we can, just by looking at this velocity time graph, this one again, we can actually try and plot or sketch the acceleration time graph. Now think about what happens to this acceleration if you see, as time passes in the velocity time graph, as time passes, the velocity increases, but the gradient, if this is just a straight line, the gradient stays the same. And this means that since gradient is acceleration, so gradient is the same as time changes. So if I want to sketch or plot an acceleration time graph for this example, okay, I can try and sketch that. Let's see what it's going to look like. Now, let me clear up some of this graph. Okay, I'll just clear the whole lot. So, let me just quickly sketch out what I had just now. I have the xt graph, which looked like this, a curve going up, and I had a vt graph, with the understanding that v is the gradient of this graph. I sketch a line going up, and then now if I want to sketch an acceleration time graph, we can do it just by looking at this velocity time graph, because we can see that the gradient of this graph remains the same, and since the gradient is the acceleration, it means that the acceleration time graph would look like this. Right? As time passes, the acceleration would just stay at the same value for this particular example. Okay, and as I've said, for a falling object, we'll learn later on that the acceleration, at least for heavy object falling on the ground, at around the ground level, the acceleration is fixed. Okay, now from this example, let's think of another one. Let's make this a little bit more complicated. Suppose that this time, okay, I can actually clear this up for now. Right. Let me think of another example. This time, now instead of dropping the ball, this time I am going to throw the ball up. Let's say with a certain velocity u. Okay, so this ball goes up, but as it goes up, it must slow down because of gravity pulling down, and then you'll turn back and start falling down. Okay, now when so at some point the ball will come back to about the same level, and it will continue falling downwards. Now I want to sketch a graph for the displacement, for the velocity, and for the acceleration for this situation, right? From when I first threw the ball at this place, and following the graph as the ball reaches the top, and then coming back to the same level. Okay, so this part of the motion. Let me try and sketch that and see what it looks like. Okay, so for the displacement time graph, t and x. So we need to define x for the displacement, right? So we need to think of the starting position. Now I would like to find an example that works. So what happens if I choose this level to be the 0 of x? I will be starting at this origin, and as time passes, x increases, and then it decreases. Is that gonna work? Yeah, maybe. So let's try this out. So I am going to take this as the start position of or the 0 position of x, and I'm going to think of this as my x-axis, a bit crooked. So that's my x-axis, and that's the 0 value of x. Okay, that's not the 0. Let's see. That's the ball. Okay, that's the ball. Okay, so if I want to try to sketch the, I'll reserve yellow for the ball, and alright, 0 there for x. So as in the beginning, alright, in the beginning, when t is 0, time is 0 at the start, x is also 0. So the ball starts here at this position, and as time passes, the ball goes up and come down. So x goes up and come down. The graph is going to look like that. Okay, go up and come down to the same level. Now, let's see. Now, if I now want to sketch the speed time graph, what's it going to look like? Let me try that. I'll draw the axis for velocity and time. Now recall that velocity is the gradient of the graph. So if I start, if I go to the starting points, okay, at the start, the graph has a certain slope. The graph has a certain slope here. Okay, I can think of the gradient of this slope here, and that would be my velocity. Now, in this case, I'm given that the starting velocity is let it be u. So there's some velocity at the start. It's not just 0 velocity. Okay. So I'm just going to say it's maybe it's somewhere here. So maybe that's my u. That's my starting velocity. Okay. And as time passes, the ball will move up. Okay, so the graph, if we follow it on the graph, the ball will follow the graph like this, and we can see that the slope of the graph decreases. All right, so when it's here, when we're around here, the slope here is not as steep as what it was at the start. And that means that the velocity is smaller, right? Because the gradient is smaller. And at this point here, the gradient becomes horizontal. Horizontal gradient means 0 gradient, means the velocity is 0. So on the velocity time graph, you can imagine that as time passes, the velocity decreases, and at some point it decreases to 0. Okay, try to sketch this. So it decreases, at some point it reaches 0, and this point is the same as this point. Alright, this point is the same as this point in time. Right, when the ball reaches the top, so the velocity reaches 0. And as the ball now start to fall downwards, we have a negative slope. A slope on this side of the graph. The slope on this side of the graph is a negative slope. Okay, because if we think of finding the gradient here, okay, for a time interval for this horizontal distance here, the vertical distance decreases, right, from there to there. So there's a decrease in the vertical distance. So therefore, this is a negative gradient, and that makes sense because on this side of the graph, it's when the ball is falling down, and when it's falling down, the velocity points downwards, so the velocity should be negative. Alright, because by choosing my x-axis this way, it means that I'm choosing up to be positive and down, the downward direction, to be negative. So beyond this time here, the velocity starts to become negative. So this means that if I want to continue the graph for the velocity, it will look like this. Velocity becomes negative, and that just means that the velocity has changed direction. Okay, now we have a velocity time graph, and this is what it looks like. And next, let me now try and sketch the acceleration time graph, A and T. That's the 0. Now recall that we have seen earlier that the acceleration is equal to the gradient of v. So if we look at the gradient of the velocity time graph, right? Acceleration is the gradient of the velocity time graph. You see that in this example, the graph is a straight line that is going downwards, and as I've described just now, this is a negative slope. So the gradient is a negative number. So if I say that number, when I plot it on the graph, is somewhere, has a value somewhere there, then as time passes, because this is a straight line graph, the gradient stays the same. So as time passes, I have the same negative gradient, and therefore the acceleration time graph looks like this. So you see, we are following very strictly the description and meanings of displacements and directions and gradients, and in this way we are able to get 3 very specific graphs that follow all the rules that we have described about displacement, velocities, acceleration, and the vector nature, the nature that they have directions.